Hello and welcome back. In this session, we are going to learn how to invert a binary tree. Let's first go through the problem statement. Here we have the problem statement, and if I maximize it, we can read it. Okay, problem statement, invert a binary tree, sample input. You see the 4 is the root node, and then the left hand side we have a 2, right hand side we have 7, and in the left hand subtree we have 1 and 3 as leaves, and in the right hand subtree we have 6 and 9 as the leaves. Now if we invert it, the root remains the same, because if you take a like a kind of mirror kind of thing, root, that's the center of the mirror, so it stays there, and then rest of the things are inverted. 2 comes in place of 7, 7 goes in place of 2, and then in nodes also 6 comes in place of 9, 9 comes in place of 6, and 3 comes in place of 1, and 1 comes in place of 3. And if you see, if we analyze it carefully, the earlier one, if we visit, like, see the left node and then the root and then the right node, and then this, if we consider this left subtree, then we visit the node again. And basically if we visit the left node, root, and then right node and complete the entire structure, then you get the numbers in ascending order actually. So it's already sorted. It's a binary tree, and binary trees are often used for to store sorted elements also. Okay, so now if you see the inverted one, it's actually, and if you visit in the same way, the left node, the root, and then the right node, 9 7 6 4, and then 3 2 1, right? So it gives it numbers in the descending order. So that's interesting. Okay, and we're going to implement both in Java as well as in Python. Very real quick complexity analysis. Time complexity is order of n, because each node in the tree is visited only once, so maximum elements in the nodes are n. Actually, n represents the total number of elements in the tree, and then the space complexity is also order of n. In the worst case, as stated in line number 21, order of h calls are placed in the stack, and where h is the height of the tree. Okay, and then this h, that is as the n grows, this is a binary tree, as n grows, h also can grow. Okay, in the worst case, everything can be in like a one side, right? One side continuously, so you might need to visit um, you might need to visit in visual, like if we see it with the eyes in the drawing, and it's fairly straightforward. If it is in one, all in the left node, or all in the right node, right, all in the one, like a, it's going like 4 7 9, and it keeps going like that, or starting from the root node, like 1 2 3 6 7 9 continuously. If it's going the right hand side, starting from 9, it keeps going like that. Visually it's easy to tell, but it may not be obvious from computer program. So in that case, we'll have to visit all the elements, and the height will also be n. So in the worst case, it's going to be order of n. So that's the complexity, both time complexity and space complexity. Now let's go back and then see our Java implementation first. Okay, here also we are trying to, in earlier videos also, there was a little bit longer for hash map implementation. We show the pre-typed code. Here also I have already pre-typed it because it's a little bit longer, and if I start typing it here, it's going to take longer, and my video size is going to be bigger than some of the platforms that allow me to upload. So let's see the pre-typed code here, but we'll run it and we'll see that. Okay, all right. Class, from the top from the top, we're going to analyze it from the top again. Okay, so tree node. Okay, what is a tree? It has a value or data. I could say this data instead of value, and then it has a, if it's a leaf node, then it only has that value. If it's not a leaf node, then it has, you know, a tree node. It has both tree, the right node and left node, or one of the left or the, either the right node or the left node. Okay, so basically this is the maximum it can have in a binary tree. This is a binary tree. Okay, so so I have two constructors. In Java we need to write constructors. So one, if it's a leaf node, I just need to set my data. It only has data. It doesn't have any other node, right? But if it's not a leaf node, then I need to have three elements. Okay, I need to have a data. I call that root, or I could just say it a node. And then I have a left subtree, which is also tree node, and then the right subtree, which is also a tree node. Okay, left in some cases left subtree might come null, in other cases right subtree might come null. Okay, and that accordingly will assign, that will be assigned automatically because we have written the code here. So this node I could have written, this root I could have written node, because when you create it, it's not necessarily every time a you know, the every time a root. Actually I could do that, you know, and if we get error, we will actually fix that. Okay, let's do that node here. Okay, so I need to replace that value is equal to, I'm going to say call it data. Okay, and I'm going to call it node. Okay, and you'll see how much changes we need to make. In that way also it'll give you a little bit better idea actually why this data. Okay, all right, we change that, and then see I had a value. Now it's no more a value here. Now it is a get data, and I need to return data. Okay, data, right, is the getter setter method, get data. And right and left I have not changed. Is a right tree and left subtree, so I'll just leave it like that. We have getter and setter method for both, and right, get right, set right. Okay, get data, get left, set left. All right, that's done. Then the main will come back because we need to first write main logic. Okay, here is the main logic. Static tree node invert tree. So what is the inversion logic? If the root comes null, so while doing inversion we basically send the root node actually. So here the naming is good. If it's null, we didn't have to do anything, we just return a null. Okay, there's nothing, it's an empty tree. Otherwise we just invert the uh, root dot get right, that gives the right subtree, and we invert that, and then we assign to this variable right in line number 60. In line number 61 we get the left subtree, we invert that and assign to the left. Okay, so basically this right and left is a, I could say right inverted, left inverted. Okay, and then in my new in my root I actually change this tree itself. My left is set by the right. Okay, that means whatever is in my right, which is also already inverted, that comes to my to the left hand side. Okay, and then whatever is on the was on the left hand side, that got inverted already, and that comes to the right hand side. So everything got inverted except the root, and we return the inverted tree because we change the memory location, right? That's how object oriented program works. And then remember here we had two extra variables here because we had to store. I could have a one temp and then I could do with only one also, but I have two, that's why it's not overwritten. I already have inverted value and I can just assign. But if I don't have these two or at least one temporary, it will not work because you'll be overwriting, and by the time you need the one, you'll be already overwriting and it's not no more available. You get a wrong result. Okay, and now we need to print, and this printing is also not very straightforward. I can just print a tree because it's a structure, right? So I pass a root and then I check if root is not equal to null, then only if it's a null I don't have to do anything. Okay, it's not equal to null. Okay, I'm printing the left node first. Okay, and then I'm printing here, look at here, I'm printing the root, and then I'm printing the I'm just going to correct this because I made modification, right? And then I'm going to print the right node, okay? And it goes in recursion. You see that if root dot get left is not equal to not, I print the root dot get left, right? And then I print the root dot get data, and then again I check if root dot get right is not equal to null, I print the get right. And it's if you see it here, uh, um, look at the line number 76 over here. Print tree is going in recursion, and this one is also going in recursion. So it's go all the way to the bottom of the tree first, toward the leaves. And it'll print the first leaf here in the lowest one in the hierarchy. Okay, in that for that node, it'll go to the leaf, left leaf, and then it'll go to the node above that, and then you go to the right one, and it will come to up. That's okay. It's recursive, so it's printing that way. I think that's it here. We covered invert, we covered print, and then now we're going to cover the main. In the main, I'm going to create a leaf nodes. I have how many? I have, let's go to the problem statement. I have, you see, 1 3 6 9. Those are leaf nodes. Okay, so 1 3 6 9, and then for 1 and 3 I have 2 as its root. We see here 2 as its root here, and 6 and 9 7 as its root, right? That's why I'm creating in line number 44 and 45. Okay, and then my tree is basically new. That's the main, the root, the final root, and the left node and right node. Okay, first I print the tree, and then I print some separated line here, and then I invert the tree, and then I print the inverted tree. Okay, let's compile. We need to compile this because we made the modification. I'm going to actually minimize this. It's coming in background, that's why. Might get error. Yeah, listed value is equal to leaf. I think that's probably is data. Let's go line number 7. Number 7. Okay, so that is data because I change this to data. Right. Data. Okay, and we compile one more time. Very good. Now I'm going to see, I'm going to run it. Okay, all right. I'm going to all right. See, it's if we see them side by side, look at that. Non-inverted initial tree. 1 over here, 1, and then we visit its node, and then 3 over here, and then the main root element. We're going left to right, left subnode, and then it's a node. Left leaf, its node, right leaf, and then we need to visit the. If you consider this as one structure, then we need to first we visited this left one, and then we visit the its root, right? And then we go to the right hand side. Again, we need to start from the left, anything in the left hand side in the tree. Okay, we visit the 6 and its node here, 7, and then we visit the right leaf. Okay, that's how it's coming here, over here, from here to here. Now in the inverted one, again we follow that. We visit 9 first, and then 9's root, and then the right leaf, left leaf. 9 is a left leaf, root, right leaf. 9 7 6, and then if this is one substructure, we need to visit, this is on the left hand side. Now we need to visit the root of that. Now this is 4. We do the same thing on the right hand side. 3 2 1. That's what we got. Correct answer. We are done with the Python implementation. Sorry, Java implementation. Okay, so in the next video we will discuss about Python implementation.